Welcome, everybody. I am Steve McCary, a platform integration manager on the strategic accounts team. And with me today is Angela Brown. Hello, Angela.
Hello, I'm Angela. I'm one of the applications engineer for the Pacific Northwest specifically. In case you're wondering, it is raining. Just to check that box off for living in the Pacific Northwest. Let's get into it. We're here to talk about acoustic echo cancellation, AEC. I'll probably use them fairly interchangeably for the class and for this hour. This is what I call, in most cases, the hour of Angela gets to talk about things she likes to talk about, but her family and friends don't let her talk about it. So today's topic is echo cancellation. We're going to do this in sort of three chunks. The first is to really talk about what acoustic echo is and what acoustic echo cancellation is, discussing how an acoustic canceller works. We're going to talk about some terms that are associated with acoustic echo cancellation, and then we're going to sort of talk about how to set up and configure the Q-SYS AEC component in Q-SYS Designer. So let's get into it. So first of all, way back in the day, back when phones had cords, we developed a concept of being able to talk to each other across distances. And then that grew into groups of people being able to talk to each other across distances. So when that happened, we sort of developed this whole industry of conferencing and conferencing technology. Methods include VoIP, POTS, Zoom, Teams, Google Meet. There's dedicated codec hardware now. And one of the big key things to conferencing is that the participants in room A need to hear and talk to the participants in room B. Participants in room B need to hear and talk to the participants in room A. And we're here to talk about how the audio challenges of that are handled by digital signal processors, by codecs, by basically all of the hardware going back to even the phone conferencing, devices that we had in our industry that hopefully have found their way out of our industry. And we're going to sort of look at that in bits and chunks. So let's start with sort of the signal pathway to this conferencing concept that we've come up with. We've got people in one room, we've got people in another room, and they need to talk to each other. So how does that happen? So we're going to talk about two rooms, and rather than calling them room A and room B, we're going to sort of call them the near end room or the far end room. The near end room is sort of what it sounds like. I always think of it as the room I'm in. So if I'm in room A and I'm trying to set up audio conferencing or video conferencing, room A becomes the near end to my brain. The far end becomes room B. If I'm in room B, I think of room B as the near end and room A as the far end. So basically the far end is the room you're not in when we're talking about this. So starting in the far end though, we want to actually sort of talk through the audio signal pathway. We have microphones in the room. We have multiple microphones in the room. We're no longer in a situation where it's one person talking to one person. It's groups of people talking to groups of people. And we have to sort of set up microphones and other things to make that happen. We're going to bring those microphone signals into a digital signal processor, audio DSP of some kind. We're going to process them. We're going to then take them, mix them down, and combine them all in a way that we can then send them out to the other end of the call or to the other room. So the far end right now is going to be talking to the near end. Remember our rooms A and room B. And so we're going to transmit that data to the other end. One quick note, transmit, I always like to just make the explanation that transmitting is encoding and decoding. So to transmit, you have to take the audio signal, encode it, send it to the other end, decode it, and receive it on the other end. Thus, conferencing codecs in general. So on the near end, in our room, in the room that I'm sitting in, as I like to call it, we have to receive the data. So it comes into our codec, gets decoded, gets then sent to our local audio signal processor, because you got to have one in each room. We mix it in with any local sources. We send it through our equalization. We send it through all of our processing. We send it to our amplifier, and then we reinforce it out of our loudspeakers. The loudspeakers in this room are a requirement, or some sort of audio reinforcement is a requirement. It could be a soundbar. It could be speakers on the sides of the display. It could be speakers in the ceiling. It could be any number of solutions. But the reason we're going to need those speakers is because we have a group of 10 or 12 people in the room. Again, group of people talking to group of people. So when you have that many people in the room, you need something to reinforce. And that sort of defines one of the big problems. Because in this room, there's also microphones. Because we have, again, group of people talking to group of people. Both groups of people need to be able to be heard. So that gets us to really our issue with echo cancellation and actually creating acoustic echo in the first place. So when the audio from the far end is amplified in the near end room, the audio is also picked up by the microphones in the near end room. That audio might also reflect off of surfaces. It might reflect off of walls. It might reflect off of the glass wall that's always in every conference room, it seems. And it's going to reflect off of all these surfaces. And all of those reflections are also going to make it to the microphone. Microphones are not very discerning. They pick up whatever audio they get sent. So that's really what our definition of acoustic echo is all of these sources coming from the far end. Basically, our source is the far end audio, and then all of these reflections and all of that data getting picked up by our microphone. This is really the crux of the thing. This is the concept, right? This is the theory of what's going on. So what we're going to do is we're going to insert an acoustic echo canceller in the audio signal path to remove that far end audio from the signal before the signal is sent back to the far end. So that way, the people that are in the far end room don't hear themselves talking. We don't create a big long loop. And then the distance isn't really important, but it's the fact that far end talks, comes out of the speakers, picked up by the microphone, sent right back to the far end. So we've got to break that loop. And that's what our acoustic echo canceller is going to do. So it's going to remove that far end audio signal. And then basically what's left over is the local microphone, me talking in the near end, and that's what the far end hears. That's our ideal world. How do we do that? Well, one of the biggest ways to do that is to provide our AEC algorithm or our acoustic echo canceller a reference signal that's sort of a clean signal that says, here's what's coming from the far end. Here's your reference. Here's the thing we want you to take out. And then once we've done that, we can, do the same input processing of the microphone in the near end, the auto mixing, encode it, transmit it back to the far end. So we've got conferencing going in both directions. Now this AEC processing really is happening on both ends. We're just going to sort of keep talking about near end and far end to make some distinctions about how the signal is being filtered through our AEC block. So let's start out with a very, very easy example of this, a very, very simple, let's assume we're in a perfect room and the direct signal from the far end is coming in. The first reflection, and just note that this little graph shows it as amplitude over time. So that first reflection is, you'll notice, slightly less in amplitude, which means it's slightly softer because the direct sound has come from the speakers above us, hits the microphone, but then that reflection maybe hits the display and comes back. And by the time it comes back, it's slightly delayed and it's slightly softer. And then say we have a second reflection of it maybe hitting the glass door that's at the back of the room. And that reflection is going to be, again, softer and slightly delayed. So this sort of graph shows our what's going on. And just consider when you're thinking through this, this is all sort of our far end audio. So what we can do is assign a reference signal to our AEC algorithm, our acoustic echo cancellation algorithm. And tell it to take that data out. This slide is going to sort of, as we do the next 3 or 4 slides, we're going to sort of show how that happens graphically. But one of the things I want to point out, and I always point out when I get to this slide, is you'll notice our direct signal has shifted a little bit. We're no longer at time equals 0 with that direct signal. We're at just a little bit out. This echo cancellation processing takes time. There is delay inherent in the processing. And everybody always asks why this delay is there. And I just am, I just want to say that, computers take time to process things, and we have to build that time in. So it's as small as we can make it. But the big point is that when my audio goes to the far end, do they really know if it's 25 milliseconds later? We're not in the same building. We're not in the same room. We're not in the same space. So we really feel like this slight delay to make the AEC processing way more effective is very, very minimal and really not all that noticeable. I mean, I'm slightly delayed coming to you, and you probably don't know that, unless you're sitting in the same room as me. So a real important thing to understand, though, is acoustic echo cancellation takes time. So the acoustic echo canceller algorithm then takes our assigned reference. We're going to talk more about the reference signal as we go along, and it's going to process out the echo, the acoustic echoes in the room. So let's take a look at how that happens. The first thing it does is it calculates the impulse response of the room. So the impulse response of the room is basically what's going on between the speaker and the microphone. You have that direct signal, and the direct signal is really speaker straight down to the microphone. And then you have all these reflections, and we have to sort of calculate what the time shift is. So how long does it take to get from the speaker to the microphone? How long does it take to get from the speaker to the TV to the microphone? And then we have to determine the time shift of those reflections, and we have to determine the amplitude of those reflections. So that's what our algorithm is really doing. The first thing that then happens is we shift our reference signal to be exactly as loud and in time with each of those reflections. Then we flip our reference signal out of phase. So as you guys all know, you take a sine wave that's starting at time 0, and you take another sine wave that's exactly out of phase, and the two will cancel each other out, and you end up with basically nothing. You've removed that audio. So basically, you're going to get this sort of sum result, as you can see on the screen, and we can actually take a quick look back here. We'll do this way. So you can see our reference signal. And our reference signal has been adjusted to be 180 degrees out of phase or out of phase. So if you go, if this signal goes down by 1, our reference signal goes up by 1. And then the amplitude has been adjusted, so they match, and they've been time aligned, so they match. And then as soon as you actually cancel them out, you have basically echo canceled out or removed that echo from the signal that's then going to go back to the far end. So if we look at this, then we actually take our next reflection. So we have our next reflection, and okay, it's a different time and it's a different amplitude, and you can see the algorithm has adjusted the reference signal to those two differences, and then it does the same thing, sums them together, removes that echo. And then we have our second reflection. And again, you'll see that the reference signal has been shifted again, lowered in amplitude to match the reflection's amplitude, and then taken out of phase, adds it in, sums those up. So I think that really sums up how acoustic echo cancellation works. Like, that is this in a nutshell. However, the important point to make here is we don't talk in sine waves. If we did, it'd be hilarious, but we don't. So if you can imagine, these signals are people talking, music playing, things happening in the room, people shuffling papers. This is not just a nice, pretty sine wave. It's a really jagged reflection of what's going on in the room. So we need to do a lot more than just this simplistic look. So we're going to actually now look at the Q-SYS AEC algorithm and AEC block and AEC processing, and actually sort of show what we do to help along the fact that the world is not perfect and everybody doesn't talk in sine waves. Although I can actually tell you, if that happened, I would be really happy and I would laugh a lot. So we're going to
Then
start
call
here.
that sign language.
Oh God, that's good. I'm going to remember that, Steve. That's fantastic. So we're going to actually talk about our algorithm. So everything sort of in blue here is a picture of how our algorithm works and the different components within our AEC algorithm. And we're just going to talk through them. So this angry person on the phone with that phone actually probably has an actual cable, is talking, and we're going to call them our far end participant, and they're yelling at us for some reason. But that audio comes in. That audio really turns into our reference in many ways, and we're going to talk about that a little bit. And that goes into the actual algorithm that's doing the sort of what we just talked about, the nudging the reference signal, changing the amplitude, changing where it time aligns. That signal, far end signal, also goes out our loudspeaker, like we've talked about. And then it also goes into something we call our double talk detector, which we'll get back to in a few minutes. The algorithm then makes the necessary calculations and sets up our filter. The adaptive filter set includes steady state noise reduction, which is something we're going to talk about as we move through the block a little bit later on, in addition to the AEC processing. Then, as you can see, our adaptive filter actually basically does that operation that we just talked about with the audio that's coming from the microphone. So it's taking these nasty little red reflections and using the reference to create those filters and then remove that audio. Once that happens, though, again, the world is not perfect. And there's always some sort of slight remnants. I mean, if you've actually dialed in an echo canceller, you will start to sort of understand, and you'll hear what I call them artifacts. In Q-SYS, we call them our error signals. So basically, after this adaptive filter has done its operation, done all the echo cancellation on the signal coming from our microphone, there's stuff left over. One of the most difficult to program and impressive things simultaneously about our AEC is that we take all that stuff that's left over and we feed it back into the algorithm. We do that so that the algorithm can fine-tune itself, so that it can just keep going through this process. It's almost like its own little personal OODA loop. Then we have, at the end of this, before our audio from our microphone goes back to the far end, to our angry guy on the far end, we have what's called nonlinear processing. So this sort of suppresses the error signal that gets back to the, let me say that again. It suppresses the error signal before it gets back to the caller's ear. Now let's talk about our double talk detector. One of the most interesting things about echo cancellation is keeping the signals, as we call them, converged. So in other words, keeping the echo properly canceled, the acoustic echo properly canceled out of our signal, so that the far end continues to hear the near end talking properly and without those artifacts or issues or double talk. So double talk, there are 4 conditions with double talk. There's the far end talking, the near end talking, silence, and then what we would call a positive double talk condition, which is both sides talking simultaneously. So imagine our little angry guy over here, and imagine me sitting in the room and I'm angry too, and we're just going at it and we're going back and forth. So we need something to stop the algorithm from working and put the algorithm on hold when we're both talking simultaneously. Otherwise, my audio will start to get removed from the signal. So we actually do this little check called our double talk detector to check for those things. silence is also a concern because silence, if the algorithm is working inside and there's silence, we want to actually sort of make sure that the algorithm isn't trying to adjust to the silence. So those two conditions really make a difference in how we're processing echo cancellation and what the double talk detector, it just continually listens for these conditions, makes a determination, and then says to our algorithm, hey, wait, slow down. One of our conditions has been met. And then when that condition is no longer met, backs off and says, okay, proceed as you were. It allows our system to stay converged, and it allows us to have a really good result with not removing signals and not echo canceling out signals that we shouldn't echo cancel out, which is such as the person in the near end who is actually talking and needs to be heard by somebody on the far end. Now, thinking our way through all of this, hopefully you guys can sort of see that this is not just taking a sine wave and flipping it out of phase and canceling it out. There's a lot more going on. There's a lot of things that are being considered and a lot of processes. There's a lot of programming. And this is a very processing heavy component in Q-SYS Designer. It's why we publish and document for everybody the number of mic channels that we can echo cancel per core, because that number is fairly finite. You can't just have as many AECs as you want because you are going to run out of processing power pretty quick. Now, imagine if there's 6 microphones and they're all doing this processing and then they're coming back and then they're being sort of summed together and sent to the far end. This is a lot. So, all right, we've sort of talked about, this is sort of our last slide on the theory side of things. Can you take a subgroup of inputs and have them process on one AEC channel? You can, but how does the AEC know that that's not double talk? So I think you actually start running into issues with that. You can try it and you can try and come up with a reference that's good enough to make that happen, but it's going to be pretty difficult. Okay, we're going to move on. Sorry, that was a question. I have the little Q&A up on my screen and somebody popped up with a question there. So we're going to move on and we're going to talk a little bit about terminology now. We've talked about the theory and now we're going to talk about some terminology. This is really just so everybody talks the same language. We all know what's going on. We all know what the theory is behind what we're doing. But I really like to make sure that people sort of understand and say the right things and say the same things so that if I'm in a room talking to you and we're trying to dial this in, we're speaking a common language, and it's really going to help sort of develop, make it easier for us to work, develop a common language for dealing with AEC. We've talked about a bunch of these already. Near end and far end. We've talked about this. I think the important thing is my AEC is for the far end. The far end's AEC is for me. And that's really the place where you need to just pay attention. But echo cancellation is going to happen in both. And again, I really just treat the near end as the room I'm in. It's nebulous, but it's not nebulous at the same time, if that makes sense. That makes slightly confusing sense. AEC reference, we'll just say that this is the information we use to tell the algorithm what to cancel out of the microphone signal in the near room. This is a audio signal that we are going to connect to our AEC block in Q-SYS Designer, and we're going to see that a little bit later on. So basically, though, you want to just think about that as this is the stuff we want to take out. Convergence is, you can read what's on here, but convergence is the how well the filter is adapting to the room impulse response. And if we get 100% acoustic echo removal, we consider that to be converged. We consider the algorithm to be properly converged. That's our goal in every case. So we're going to then talk about latency. We talked about it a little bit before. AEC takes time. But taking a look at what the actual latency is of the cores that we have is pretty important. You can read that on the slide. My biggest thing is everybody gets really concerned about this latency. Does the far end know? I think if the far end can hear a delay, we need to look at figuring out why and what's going on. But in general, this is almost a transparent latency, but there is latency there. AEC takes time. That processing takes time. Tail length. So I'm going to say this, and I say this in one sentence, and it makes sense to me. How long after our initial direct signal the system will look for reflections to be canceled out? That can be in a Q-SYS core 100, 200, 300, 400 milliseconds. We're one of the few cores that gives you access to this. Most audio DSPs really operate somewhere in that 200 millisecond range. I'm sure everybody's algorithm is slightly different, but 200 is really our default and kind of a starting point. I would say 85% of the AEC that I've done can be done with a 200 millisecond tail length. Why would we want a longer tail length? I think that's actually also worth talking about. If we're in a really big room, so think not in our conference room anymore, but say we're in a training room and the room is bigger, it's maybe 50 feet by 50 feet. The acoustic echoes are going to take longer to come from the speaker, hit or bounce off whatever they're going to hit or bounce off of, and get to our microphone. So if we have a longer delay or longer time between the direct signal and our reflection signals, we need to have that longer time where it's looking for reflections to be canceled. The times where I've used a longer tail length are in bigger rooms, in training rooms, in auditoriums. Just be aware though that like I tell everybody to start with 200 and see where you get. The more you go up in tail length, the more processing this takes, because the longer the algorithm is working on that signal. So it's gone from 200 milliseconds and it's double the amount of time that it's working on that signal, which means that with the finite amount of processing we've got, that you cut the number of AEC channels you have available to you in half. So I'll give the example with a Core 110F. You have 16 channels of echo cancellation at 200 milliseconds, but only 8 at 400 milliseconds. So as you're planning and designing your systems, be very aware of the size of the room, whether or not you think you're going to use a 300 or 400 millisecond tail length. I know that was a lot of explanation, but understanding that and understanding that you can change that setting as you configure your system is very, very important for processing power and understanding how much capacity your DSP has. All right, next one. The reference to microphone level ratio, or RMLR, just rolls right off the tongue. We have this ratio because we essentially want to know the difference between what's being heard by the microphone and what's the reference level. So it's going to be basically the level of our reference minus the level of audio from the microphone. We'll just talk through the math of this example. Our reference is minus 20 dB. Why is it minus 20 dB? Because that's unity gain in a Q-SYS core, and we want to get that to be as close to minus 20 dB as we can get it. And then, so the reference is coming in, it's minus 20 dB, and our microphone is picking up minus 30 dB. So minus 20 minus 30 gives us a difference between the two of 10 dB. And you can sort of look at that and understand it sort of intuitively that the difference between 30 dB and 20 dB is 10 dB. We want to, in our echo cancellation, really, really target getting that as close to zero as we can. We want what's coming from the microphone to be as equal to what's coming from the reference as we can. Brandon, yes, it's 20 dB or minus 20 dB FS, because FS is digital, right? DBU is analog. So it is minus 20 dB FS. So just pay attention. This is something that you're going to see quite a lot. You're actually going to see a nice little bar that gives you a green indicator when you're doing it right. But even if you're not, we want to target that 0 dB. So RMLR, reference to microphone level ratio. Oh, I went too far. The next one is echo return loss enhancement. So this is a representation of the amount of work being done by our AEC algorithm. It's the difference between the level of signal at the input of the block and the level of signal after the AEC processing is complete. So in our RMLR, we've been dealing between the reference and the microphone. Now we want to deal with the microphone to basically the microphone post cancellation. How much cancellation is taking place? How much audio has been removed from the microphone signal? So this is also a simple sort of math. I mean, this is pretty simple math, but our microphone level is still minus 30. And the audio after the AEC algorithm is complete is minus 50. So the difference between those, the delta between those, minus 30 dB minus 50 dB is 20 dB. And again, you can sort of see that. Like, you don't have to do this weird formula with all the minuses in it. You can, but you can just understand that you are removing basically 20 dB of audio from the signal. I think that's about it for that. This is something that I don't pay as much attention to. The RMLR is something you really pay attention to, but this is something that's nice to know and to understand, because you do have a measure of how much work your AEC algorithm is doing. And you can make a case to go back and say, well, it's not working because, my AEC has to remove 50 dB of audio just to get anywhere close. And maybe we should put some acoustic paneling on the wall, kind of a situation. So then we've got a couple more definitions. Another really important one is residual echo suppression. So remember back in that diagram, we had our nonlinear processing. That's what this is. We call it residual echo suppression. It's basically taking out the error signal after the AEC processing is complete. Cool thing is we actually, in our AEC block, give you guys some access to adjust this. So you can make some minor tweaks and adjustments. And it's really interesting to see people, if they're like, oh man, I need to take the tail length from 200 to 300. Well, why don't we keep it at 200 and try adjusting the RES and see what happens, and see if we can actually get some of that, those final little bits of artifacting out before we actually change our tail length. One quick note, nonlinear processing. I just wanted to, I think every single class I give, I'm just going to define this. Nonlinear processing means that different things are being done to different bandwidths or frequencies in your signal. And in fact, this residual echo suppression is a nonlinear processor. We have lots of other nonlinear processors, our feedback exterminator, all those other things. Be aware of what's linear and what's not linear. Linear is like a gain knob where you take all of the signal and add 3 dB, or all of your signal and add, 6 dB equally. Nonlinear is we're chopping up the signal into little bits, and in different frequency ranges, we're doing different things. So maybe at 100 hertz, we're going to remove 6 dB, but at 2K, we're only going to remove 2 dB. That's non-linear processing. And this residual echo suppression is in fact non-linear. Like, it can't be linear because all of a sudden it would get really, really choppy for the audio going to the far end. We're trying to do, in my mind, as little as possible to get rid of that error signal that is left over after AEC is complete. All right, voice lift, or as I call it, reinforcement, sound reinforcement. And honestly, we see this not just in large rooms. I like it. I like what it says on the slide. In large rooms where the near end microphones are sent to the speakers in the near end room. Anything that's being reinforced locally. We talk about this because this becomes a problem, right? All of a sudden, I'm being reinforced in the room that's doing the same loop that our far end audio is doing in terms of getting picked back up by the microphones. So we have to be very careful and very deliberate about how we process those and how we assign reference signals to them. So mix minus, I actually have some notes that I'm looking at, and I just put crazy local reinforcement in my notes. Mix minus is really a situation where you have a lot of localized speakers and a lot of localized microphones, and you want to make sure that the localized microphones are being heard everywhere where they're not localized. So imagine a council chambers and there's 20 people on the council and they each have a little gooseneck mic. And they each have a little speaker so that they can hear and they can adjust their own little volume. My microphone and my little speaker in front of me, I don't want my microphone to come out my speaker, but I want my microphone to come out all the other speakers. So basically, my mix is all the microphones minus me. So mix minus. That's kind of where that comes from and how that actually happened. I actually think there's a broadcast term that goes along with that, but essentially that's what it is you're listening to a mix minus yourself. Andrew, we'll get to that. I'm going to read Andrew's question. Best practice, put voice lift microphones in a separate AEC block from anything else to process it differently. Yes, I mean, typically yes, or you want to give every microphone that's being live reinforced its own reference signal. Like you can do a channel by channel reference, and that's a setting that you can select in the AEC block. So you can either give them their own reference or put those in their own AEC block, however you want to do it. There's a lot of leeway and a lot of ways of doing it. And I would bet that even between me and Steve, that we both have different preferences. So I think that that's one where you're going to figure out what works best, and really paying attention to what's coming out your speakers is really the big important point that we want to make, is understand when you're using voice reinforcement, when you're doing these sort of mix minus systems, that all of a sudden the complexity is equally as complex when it comes to acoustic echo cancellation. All right, so we've done all of our definitions. Whew. I really feel like maybe the definition should be at the beginning of this, and then we should talk, but either way. So now we're going to start talking about like practical application. And in order to do that, we really have to sort of start with how our signal flow happens inside Q-SYS Designer. I do want to note that a lot of the things we're going to talk about next are all very Q-SYS Designer specific, but the concepts behind them can be applied almost to any DSP platform. It's just the blocks are going to look differently, and maybe the things are going to be called different things. So don't be afraid to think through this process and think through these signal pathways wherever you are and whatever you're programming. So we're going to talk about this. And let's start with our sort of path to the far end. The path to the far end starts with my microphone, the microphone on the near end. So our microphone is coming in, it goes into our acoustic echo canceller, comes out, it goes into a mixer of some kind, a gain sharing, a mixer, just a mixer, a gating mixer. We tend to like gating mixers, and for a very specific reason, which we'll talk about here. And then it goes to the far end. And then we have our path in the room. The far end audio comes in. Maybe we have some program audio sources like a laptop input, and all that gets mixed down and it goes to our loudspeakers. So far end comes in, mixes in with local sources, goes out to the speakers in the room. Notice how that output to the speakers in the room also becomes our reference signal. Pretty interesting. We're going to talk more about that. One other thing to talk about with the gating mixer. There are gain sharing mixers, there are gating mixers, they're just regular mixers. One of the reasons we like the gating mixer, and we show it in this example, is because you can leave the last signal open. And that last signal staying open means that audio still goes to the far end, and it doesn't like just cut off and make you feel like somebody's hung up on you. And I know that's sort of less and less of a thing, but back when those of us who are old enough used analog phones, that dead silence was very concerning because it meant you've been hung up on. So one of the cool things about the gating mixer is you can leave that last mic channel open, or the last channel that opened or last gate that opened, leave it open so you have some small measure of noise that ends up going to your far end. And it really makes everybody sort of understand that the call hasn't been hung up or there's no technical issues or anything. So something that we quite like. Anything else I think we need to talk about? I don't think we need to talk about any of this. So we've talked about that. Great. Let's move on. We can turn off our little pointer. All right. So let's talk about microphone processing. When we bring in our microphones, we definitely want to do something to make them sound good. Leaving them unprocessed is maybe it's fine if you've got a fantastic microphone, but when you start getting into microphone arrays and table microphones and all of those things, there's a lot of processing that we actually want to do to make it sound good to our far end participants. So we're going to insert processing. I think the big thing about this is thinking about where you put this processing. We recommend putting it after your AEC block, especially nonlinear processing. Remember back to that nonlinear thing? As soon as you start doing nonlinear processing and then sending that into your AEC can't keep up. The algorithm that's trying to do nonlinear processing is trying to operate on nonlinear processing. And just trust me when I say that turns into like that ball of yarn that you can't get an end out of. So being very aware of where you put things, being very aware of what processing is linear, what processing is nonlinear. As we all know, compression is linear, or compression is nonlinear. My apologies. So just be aware of that. One other thing that we want to talk about with microphone processing is where you mute. This has become a little bit less of a thing because we've actually given you some settings in the AC block now to handle this. But if you mute your microphones after the AEC block, it allows your AEC block to actually stay converged because it's still going to get the reference and it's still going to get the microphone audio, and it can stay sort of in sync and working even if your microphones are muted. So something to be aware of that, muting the microphones to the far end can happen anywhere in your signal path. And I think that's the important thing to really make a point of. Obviously, we all have worked with the ceiling mics, the Shure's, the Sennheisers, the Audio Technicas. And a lot of times when you want your light to change colors, you're going to put your mute wherever you put your mute, right? But I'll just say this, and it's something that everybody should be aware of. The light on the microphone and the actual muting of the microphone are two independent controls. So if you really want to play around with that, you could actually have the mute happen somewhere in your file, and then you just tell the microphone what color to change to. So there's a lot you can do with that. And I think that point is just worth making. Talking about all those microphone arrays, we want to recommend that you follow their guidelines, which means that quite often there is going to be some equalization that happens before the audio signal comes in. And Rick, I think that's a really big point that you're making where you say, I like to put a high pass filter before the echo cancel, to keep garbage out before it even gets to the AC block. A lot of times that's when you get into ceiling mic arrays or any sort of dynamic mic array that you really want to follow their prescriptive setup. Like back in my day, the original Shure MXA 910, when you mounted it in the ceiling, they had a whole document about how to EQ it and how to make all those changes. You did all that in the microphone before the audio even hit your AC. So technically, you were EQing that before it hit the AC. Just be really aware of your nonlinear processing. The AGCs of the world, the compressors of the world. Think about those things and be deliberate about where you approach putting them in your file and in your signal pathway. I always look at this slide too, and I just want to make the common sense comment that compressing a bunch of audio signals before you send them into a gating auto mixer is also something you should think about. Whether or not you really want to do that, because the gating auto mixer needs level differences in order to open the gate. It needs to know, oh, this one's 10 dB louder, I should open that gate. and if you're compressing everything down. So again, just another example of taking the time to pay attention to your signal pathway. I know we're spending a lot of time on this, but it is very, very, very very, very worth it. Brandon, I'm going to grab your question. So true, dead silence is bad. Doesn't gain sharing also prevent dead silence? I believe it does. I'll be honest and be really forthright that I use gating mixers 95% of the time and very seldom use the gain sharing, but I believe it does as well. I think you have the ability to sort of keep that little level of noise. And if not, you can always do something to make sure that noise is there. I've seen people add, sidechain noise just to ensure that that doesn't happen, but you can do it however you'd like to do it. And yes, I believe your gain sharing also does that. Okay, so then we're going to talk about unity gain. We talked, I don't know, 15 minutes ago about unity gain in the Q-SYS ecosystem being minus 20 DBFS. We really, really need to make sure that our signals are unity gain. The echo canceller really wants to operate at unity gain. It does its best work. When I was learning to mix, somebody always told me that you mix at 0 dB because those incremental changes allow you to mix better. It really is just making sure that we've got unity gain. Making sure also that user controls, those gains are in the right places to make the echo canceller work properly. You'll notice we have our gating auto mixer, and then there's a gain after that. That gain after that is something that the user might control or that you might set in order to get USB audio level properly through to the other end. Be aware where you're putting that. Don't put that somewhere where it's going to cause the echo canceller algorithm to fail. All right, our AEC reference. We've talked about it a lot. I always start out telling people, if your reference is what's coming out of the speakers, that is your best place to start. What goes to the speakers goes to the reference means that basically we're giving a microphone a blueprint of, hey, this is the stuff coming out of this speaker and coming right down to your microphone. Take that out. So you almost can't go wrong. And a lot of times if you're struggling, take a few minutes and step back and think about it. Like if you have audio going to your reference and then after the audio goes to the reference, you've got all kinds of speaker processing that's going on. And now what comes out of the speakers is totally different than where you've sent the reference. You might have artifacting and you might have a lot of things going on. Other things, let's see. All the far end audio definitely needs to be part of your reference. And if that's what's coming out of the speakers, again, that's going to give you a good thing. We want to make sure that program sources that are also routed locally out of the speakers are also in your reference. So generally you're going to come up with some kind of a mix for your reference. But, to me, the closer you can put that reference signal to what's going out of your DSP, the better off you're going to be and the less you're going to have artifacts. Placing a microphone signal into its own reference is bad. So that's going to tie in, Andrew, to your question. How does that change affect audio to the far end with voice lift? This is where you're going to be doing channel by channel references in your DSP file. Because you're going to have to create a reference signal that doesn't have my own audio in it, right? So I've got 4 handheld wireless mics. They're being reinforced in the room. They're also being sent to the far end. Microphone number 1, we can't reference itself back out, but we want to reference out microphones 2, 3, and 4, plus the far end, plus all those other things. So you can see that microphone by microphone, you're going to really need to create your own reference mixes inside the DSP so that you can make sure that each channel, each microphone that where audio is being picked up gets referenced properly. Does that make sense, Andrew? Hopefully that answers your question. Okay, so near end signal path. This whole slide is this whole slide is in a nutshell a slide that says if you're going to give somebody a source volume control, make sure it's before your reference signal. That's all this slide is saying. If I have a user volume control for that wireless microphone, so our example where we have 4 wireless microphones, and I have a volume control for that microphone, I need to make sure that the signal that I'm sending to my reference is after the volume control on the touch panel for my microphone. Because if I raise my microphone, I need to raise the reference. So if we just make sure that we put things in the right places in our file, and that's what this slide is saying, is if you're going to give volume controls, make sure those volume controls are upstream, as it were, of your reference signal that's going back to your AEC block. All right, so now conferencing system setups. Now we're going to get into some setup, and we're almost done, folks. This has been good. Now that we've wired it, now that we built our DSP, now that we understand how it works, we really need to develop a repeatable process for configuring systems. You want to develop good habits, you want to develop muscle memory, and you want to be very prescriptive about the steps. So we actually identify these steps. I know that it seems silly to tell you to set your gain structure before you dial in your AEC, but again, build the muscle memory, build the good habits, build this systematic approach that as you go into a room here, you go into a room here, you go into a room here, you're doing those same steps and you're really understanding how they all affect each other. So first step, now that we've hooked everything up, we've pushed our file in, we need to set our gain structure. Again, minus 20 DBFS. We want everything to be minus 20 DBFS. We want to process everything through our DSP as close to unity gain as we can get. That includes Dante mics. That includes all our ceiling mic arrays. That includes AES 67 signals. Take the time to set the gain on, say, the wireless receiver. And then when it comes in, you've got another preamp gain here. You've got digital gain. You've got all manner of things before you start actually doing stuff in the DSP file. Take the time to set that. I would say about 20% of the time when people have issues with AEC, I go back and I set their gain structure, and a lot of those issues start to just sort of go away as the AEC algorithm can process properly. Okay, item 2, signal to noise ratio. Signal to noise ratio is the difference between the background noise in the room and your signal and your mic signal. We want that to be greater than 15 dB. So doing a little bit of math, if our gain is set at minus 20 dBFS and we need a 15 dB gap between the noise floor of the room and our signal, we need our noise floor to be minus 35 dB or lower. And that's really important. That's just good signal to noise ratio. But I've also seen, again, in rooms where they're having issues with the AEC, where all of a sudden their noise floor is too high and they're struggling to make the AEC algorithm work properly because of that signal to noise ratio not being correct. That's where you've got some ammunition. Like if you can take these 2 screenshots and show that your noise floor in your room is too high, go back and talk to your architects and talk to your customers and say, hey, listen, we're going to really struggle in this room, and here's why. It gives you something specific to hand to a customer to say, hey, we need to fix this thing. All right, so we checked our signal to noise ratio and we're good. Next thing is we're going to set outputs. This is a step that with the advent of DSPs, people tend to not do this step. Take the output all the way down on your output block in your Q-SYS core, making sure you've got your nominal gain or unity gain all the way through that. Use that output and use that gain right there, that analog gain, which is called max RMS, to really set your levels in your room. In conferencing, I think we target 70 to 76 dB SPL in the room as sort of a really comfortable, and there's a lot of like theory and math behind that you can go look up, but essentially it's like the noise of humans being humans is X, And then in order for conferencing to be comfortable, you need to be X plus whatever that number is. And in general, that gets us to that sort of 70 to 76. I used to work on the end user end, and we actually used 74 as our target number for setting all these rooms. So set your output levels. I think the big thing here is like, you've set your input. Don't forget to set your outputs properly. You know, one thing that Q-SYS does is that max RMS is all the way up. So like, make sure that you actually adjust and make sure that you're paying attention and make sure that you're not blowing things out of the water. And if you take our gain structure webinar, you'll really understand that a lot better. But I think here in this one, we just want to say, be very careful. If you're blowing your speakers out of the water, and if you've got 120 dB and it's so loud that your reference signal is so loud, you set yourself up to have a really poor echo cancellation experience all the way through the pathway. All right, so then let's get to step 4, make a test call. One of the other things that I see people forget to do a lot is to set the incoming audio level of your call before you try to configure your echo cancellation. So get on a test call, have somebody that you trust on the far end to just talk in a normal voice, or you know, have a couple of people in the room, whatever you can do, and set that incoming audio level. Once you've got that incoming audio level, we can kind of move on to our echo cancellation block and set that up. And now we're getting into the good stuff. So in the echo cancellation block, we're going to talk about a couple of things. One, this noise reduction enable level. Noise reduction, think of noise reduction for steady state noises, air handling noises, a low hum, like say there's some mechanical thing that's causing a low hum. That's what this noise reduction does. This setting, these two things that are circled here, the noise reduction, that's what you want to use that for. So if you get on a call and the far end is like, man, all we hear is whoosh, that's where you want to turn on your noise reduction and actually take some time to try and mitigate that as much as you can. Be careful. Noise reduction is noise reduction. It's not a very smart thing out there in the world. So too much of it, and you could actually make the quality of audio on the far end be pretty crappy. So just use at your own discretion and think steady state noises, low steady state noises that we just want to take 2 or 3 dB. It helps, you know, helps make our conferencing sound a little bit better. Then our RMLR, remember that? Rolls right off the tongue. I'll get to your question here in just a second, Preston. The RMLR, see that target 0 dB? We even tell you what the target is. I think the best thing that I can actually say is green is good. If you're in that green range, you have a, let's just say, a happy AEC algorithm. But this is where you can actually set that. The nice thing is we give you reference gain, so you can adjust the reference gain in the block in order to get yourself as close to that target of 0 as you need to. Our adaptive filter. This is what I was talking about, where like we've given you some provisions about muting the microphones before the AEC block, or actually accidentally muting a signal that's going back from the reference. These things are, just read it what it says, hold if mic level below. So what we recommend with the mic level is set that before, just a little bit below your noise floor. So basically, if your mic level goes below the noise floor in the room, stop processing. You know, hold on, wait for that to come back, and it allows the algorithm to stay converged a little bit better. Same thing for the hold if reference level below. If that reference can get muted in some way, it allows you to sort of basically make sure that the system stops trying to converge and just pauses and waits for that to come back. So then our residual echo suppression, remember, our non-linear processing. We give you the controls for that. Enabling that allows you to then sort of adjust to try and get that more of that error signal out of your pathway. Be careful as you increase that, though. It's going to turn your conferencing from full duplex to half duplex. And just for fun in a room when you're testing sometime, take that all the way up and hear what it sounds like so that you know never to do it again. It's going to be interesting. And I can just say, one of the things about this residual echo suppression is it might be different in different rooms or different microphones. If you have a microphone over here and a microphone over here, they might be getting different echoes. So find a good medium ground, or if you have to, use a different AEC block for that microphone. That's where I would actually look at, wait, I have a microphone, or hell, move the microphone. All right, I'm going to answer your question. We'll talk about double talk just a little bit after that. Preston asks, so if you are using USB out of the core and you are using Zoom on the computer, do you need to use AEC in a DSP? We recommend it. I think that the AEC that's built into Teams, built into Zoom, built into Google Meet, it's meant to handle a single microphone and basically your laptop. When you get into more complex systems and multiple microphones and multiple reference signals, those systems can't handle it. If I'm using just my laptop, like right now, I don't have a DSP in line and I'm just talking to you through my laptop, Zoom can handle it fine. But know and understand where those limitations are. All right, next one. What kind of artifacts would you hear if the adaptive filter settings weren't adjusted properly? You're going to hear things like that you're going to hear some robotic sounding things. You'll hear, like I'll be talking and then I'll stop talking and you'll still hear a little bit of audio there. That's some of the things that you're going to hear if your filter isn't actually doing its job or you've got something that's not quite right. If it's really off, the far end will just hear themselves talking. So it'll be like, I'm going to say something, I'm going to say something, I'm going to say something, and you just hear yourself slightly delayed as it makes the loop and returns back to you in the pathway. Brandon, as a feature, why not automate setting of reference gain to get RMLR as close to 0 dB? Is there an advantage to giving this control to users? I think so. I think giving the control to users, or programmers, I should say, like you're never going to put that on a touch panel, gives you the ability to do individual references per microphone. And I think that would be really hard to automate, especially if it's, say, a wireless microphone that might move around the space. I don't know how you'd automate that. I'd be willing to look at that, though, because, boy, that would make a whole lot of us DSP programmers a whole lot of happy. Last thing, double talk. So when you've set your residual echo suppression, test your double talk condition. If you guys are both talking and you guys are both, say your far end is talking and you're talking in the room, hear what that does to the far end audio. And this is a place where you can actually sort of adjust the residual echo suppression just a little bit more. Double talk is one of those places where you're going to create the most errors coming out of your AEC algorithm. So it's a good place to stop and test your double talk. All right, we've gotten through the bulk of it. All the hard things we've gotten through. Then at the very end, we've done all our steps. So we've set our gain structure, set our signal to noise, configured our outputs, made a test call, set up our AEC. And then we have to repeat this process if we have multiple codecs, multiple conferencing systems. Don't forget your VoIP if that still exists in your system. You have to set that on basically a per codec basis because you have different far ends. So just make sure that you actually go through all these steps and be deliberate about all those steps for all the different applications that you're running through your core. All right, so then let's talk about troubleshooting. This is where it gets good. I'm going to actually take a second when I'm going to answer Patrick's question. So when using microphones for reinforcement, where is the best place to grab your signal that will be reinforced? Before the AC block, off the reinforcement outputs of the AC block, or somewhere else? Patrick, that's a preference thing. I can tell you what I do. I always, if I have a mic that I know is going to be live reinforcement, I split it right off the input coming into the DSP. But You can absolutely use the reinforcement outputs of the AEC block. I don't. And it's more that I spent a lot of time not having those reinforcement outputs on AEC blocks, and I just got used to programming it a certain way. I also think that it allows you to, again, remember AEC processing takes time. AEC takes a little bit of time no matter what. It allows you to make sure that you can time align those local sources, but that's just what I do. And again, I bet if Steve unmuted, he might do something entirely different. This is one where this is experiential, right? You've got to do it to really know what you want to do when and where.
Honestly, this is one of those things where Dan and I have likened this a lot to to an art form where there's no quantitative way for me to say, we talk about this a lot in gain structure, and we talk about it a lot in this class as well. We also talk about it in the dynamic audio processing class when we're talking about compressors versus limiters and expanders and gates. And it's like, well, it really just kind of depends on what the room sounds like, how everything is configured, how everything is set, all of those things. So yes, I agree with Angela. Early in my career, Angela and I have don't let her baby face fool you. Angela and I have been doing this about the same amount of time. I just look like I've been doing it longer. And we remember AEC without these reinforcement pins, and you had to do it manually. I mean, it's like, I remember doing room combining manually without a room combiner block. So you might see us do things one way. The reinforcement pins on the AEC block, again, it's not a broad brush. It doesn't necessarily work with every configuration in every scenario. So this is why we like to set up these webinars and really go through, what all the knobs do, so that you have an idea. And when you get into a room, we can give you, the best practices, but that is not necessarily the solution every single time. So we're really here to arm you with the information and then, turn you loose in the world. We kick baby bird out of the nest, and then it's time for you to, do it on your own. And the more you do it, the more comfortable you'll get with it.
Thank you, Steve. Did I throw that one to you? Throw you to the wolves? I think the last, we're just going to take a few more minutes and we're almost done. I really think that the last couple of slides are really about troubleshooting and really about just checking things, checking routing, checking gain structure. We used to have a Cisco codecs used to actually create a loop if you use their reinforcement output. There's all sorts of those things that you want to do. And I think, to me, it's building the good muscle memory of doing it right way, doing it the right way, and doing it the right way. And then when something's wrong, you can be like, oh, at what step did it go wrong? I'm going to go look at this thing. And troubleshooting, to me, is about that. It's about muscle memory and good habits. If your gain structure has been set all the way through your DSP, you've probably checked your routing of all your signals. And you probably know that a signal is not going where it shouldn't be going. But I'll give you an example. I was on a call yesterday, and the end user was like, hey, the audio coming from my DSP, I've got just this 20K tone, this signal that's coming in. And we actually figured out that he was creating his own loop. The output of a mixer was feeding back into the input of a mixer, and he just had a little loop going on. And taking the time to check those things. So one of the things when people are having issues with echo cancellation and signals coming from DSPs, or sorry, not DSPs, codecs, one of the first things that I'll do is I'll just start tracing the signal. And just be aware, the hover monitor is your friend. If you're connected to the core, you can pin the hover monitor and hear the audio through your laptop loudspeakers if you want. Use the tools that we've got in there. Use those test tools that we make you put in every single file and get grumpy when you don't. Those things are really incredibly useful and can help you identify problems in your signal pathway that can create problems in your AEC processing. So then what if there's still problems? What if it doesn't work? I think Steve and I have both talked about it. Steve really just hit on a lot of these things, is knowing what tools to kind of throw at this. I always like to give an example. I did a training room in a room in Mexico City, and there was a podium mic, there were 6 wireless mics, and there were 4 ceiling mics. And it was just a big square room, nothing fancy, nothing, and luckily nothing glass. And I ended up with 3 different AEC blocks, one for the ceiling mics, one for the wireless mics, one for the podium mic, and 3 different reference mixes. Um, that's great, but you might large room. I'd say large room, 50 by 50. I tend not to think of a room size, particularly in dimensions. I think of it more in people capacity. And that's probably not the right thing to do. But like, a medium conference room to me is like 10 to 14 seats, a large conference room, say 18 to 24 seats, or that many people that are in there. A training room is something where you might have participants upwards of 50 to 75 people. That's sort of where my brain goes with that. Thank you for asking. Um, and I ended up with different AC blocks, and a lot of it was based on what my reference was and where my reference was. It also is sort of based on knowing how much processing I've got in my core. Separating my wireless microphones to a different AEC block allowed me to set the tail length differently than the ceiling mics because the ceiling mics aren't being reinforced back into my room. So they really don't need a long tail length because they're not actually being heard. They're just picking up audio. So I was able to set that to 200, and I think I had my wireless mic set to 300. And then the podium mic was just such a different gain. And even setting it at unity gain, when people are backed away or brought forward, or it was just so out of bounds, not really relevant to the other 2 sets that I ended up with a third AC block just for that one microphone. So be aware of being able to add those tools or change those tools. Hopefully this webinar is giving you some of those tools. I will say that if if you have a room and you've set it to 400 millisecond tail length and it's still not echo canceling properly, there's something else wrong. And know what those triggers are. Know what those signs are of something not working, where you can go back and again be systematic, be deliberate, and build those good habits. Then if all else fails, don't be afraid to go and talk to people about the room you're in. Trying to do echo cancellation, everybody thinks that it's just something that magically happens when it's not at all. And you can be in a room with 4 glass walls and you're never going to win. You're never going to be able to echo cancel out enough of that. So being able to give very concrete answers, which I hope I've armed you with in this webinar, to people like architects and customers about why it won't work and what's going on in the algorithm that will cause it not to work. Like you can't have too many reflections. The system will just not work properly. After 200 milliseconds, it's going to stop trying to cancel that signal out, or 300 or 400. And if 400 doesn't do it, you've got to go back and start talking to the people that built the room. So hopefully this gave you a better understanding of what echo cancellation is, and hopefully gives you a better idea of some things to do to make it work better, and how to approach the folks that you're talking to when you're trying to get these rooms designed and built. All right, can steady state noise in the reference cause issues? Yes. Just simply put, yes. You want to avoid that if you can. You don't want that non-audio or non-microphone signal to try to be canceled out all the way through the pathway. You're going to make your AEC just work really hard to answer your question. So cool. I'm only 15 minutes over. Is that pretty good? I think that's good. I think we did okay. I really want to take a second and really appreciate everybody that attended. Thank you for coming. Thank you for listening. And hopefully we see you at another one of these again in the future.
Yeah, one last thing, because this will pop up a couple of times. In the next week or so, you will receive a copy of the slide deck. You'll get a recording of the webinar. All of that will get sent out to everyone that registered, which is another shameless plug for these webinars every week. Even if you cannot attend live, go ahead and sign up and register, and you'll get a recording of it within a week or so. It depends on how busy marketing is and how long it takes them to package it up and send it out to us.
Awesome. Thank you.
All right, everybody, have a great week. Thanks again for showing up, and we will see you next time.
Have a good one.